Hey, this is Horner. This is a messed up question. I like it though. This is rotational dynamics, free response question number 3. And the thing that you have here is a wheel. Okay, it's really thin, has a radius of r, and then you have some beads, and these mass beads are in massless rods, and they are little r, and they have this mass here, which is 4m, connected with a string and wrapped several times around. In case 1, this student places the beads really far from the center, and they give it an initial clockwise speed of omega naught. So that's it's going this way, so they're going to push it this way. They want us to graph this. Now, normally, that would mean clockwise is negative. So normally clockwise is a negative value. However, they said allow positive values of rotational quantities to be clockwise. So they have totally gone against convention. That means that you have to make sure you read the question. Because I did this wrong and then went back and saw that this says positive values. So anyway, clockwise here incorrectly, if you base it on what we normally do, is positive, but we're going to leave it. In case 2, the student makes it go counterclockwise, which in this case will be negative, and when they make it go that way, then the weight pulls down and whoa, then it goes back the other. So it initially will go this way and then stop and then come back and go the other way. So that's kind of the motion for case 2. In case 1, it has an initial positive velocity, angular velocity, and then it's going faster. And then this one's going to be steeper. Why is it steeper? Because now you give it that negative velocity, and it compensates and then makes it go positive. So our acceleration in this one's going to be bigger than it is in this one. So this one starts higher, but then it doesn't need a lot of help to get going. This one starts left, and that weight counteracts it quickly, and so it's going to have a bigger acceleration. So here is number 2 acceleration. Here's number 1 acceleration. Notice that I went over 1, 2, 3, 4 boxes. I can only go over 1, 2, 3, 4 boxes on this one, so I need to extend these lines over. Whatever I do here, I have to make sure my time is the same here. It would not make sense to go any further than that. You get 4 points for doing all those things. Next time it says a student performed several trials in order to vary the value of r. So here we're varying the value of r. Each one, the beads have the same radius from the center, but that radius changes from one trial to the next. The student takes data on the acceleration of the block and the tension in the cord. So you see these 2 graphs, you're not really sure what's going on, but they want to know which one is a graph of acceleration versus radius. So as you move further and further out, notice the acceleration is going to get less and less because that wheel has more moment of inertia, and it's higher, it's a lot tougher for it to accelerate. So the further apart the spheres are placed, the higher the rotational inertia, and if you have a higher rotational inertia, it is harder to accelerate the wheel. This one's got to be tension versus the radius, and tension opposes weight, that reduces acceleration, and the less that block accelerates, the greater the tension must be to oppose that weight. So that's why this one is tension versus the radius. The final trial that the student took was where r is equal to r, so the beads are set on that really just on the outer rim. So they want to know which describes the tension in the cord for this trial. So the tension here has got to be less than the weight of the block. The block is accelerating downwards, so because that block is accelerating downwards, your mg has got to be greater than the tension. So your mg down has got to be greater than the tension up, so your acceleration can be down. They next want to know what is the acceleration in terms of gravity, and it will be 1/2 the value of gravity. Here's why. Your 4m block plus all 4 of those weights, all of the masses have the same acceleration. So the weight force has got to be 4 mg. We know that force is equal to mass times acceleration, so now we have 4 mg, which is the weights, and then we have 8 times mass times that acceleration. So that's where this comes from. So this is equal to 4 ma. Sorry, 4 plus 4 is 8, not 4. So that would be 8 ma. That's where the ADMA comes from. The weight force is 4 mg. They are equal here and opposite, but if you do if you get rid of the m's and then you do a proportion, you'll see that this will be 1 g over 2a, so it'd be 1/2 g for every a that you get. And that is the end of this somewhat